First, toward a quantum revolution for computing. We'll hear from Krysta M. Svore, who received her PhD from Columbia University. She's a principal researcher and research manager at Microsoft Research, where she leads the Quantum Architectures and Computation group. Her research has included the development and implementation of quantum algorithms, including the design of software architecture for transmitting a high-level quantum program into a low-level, device-specific quantum implementation, and the study of quantum error correction codes to enable fault tolerance and scalability. Dr. Svore has also developed machine learning methods for web applications, including ranking, classification, and summarization of algorithms. She's a senior member of the Association for Computing Machinery, serves as a representative for the Academic Alliance of the National Center for Women and Information Technology, and is an active member of the American Physical Society. She currently serves as chair of the steering committee for the Quantum Information Processing Conference and is chair of the Board of Trustees at Forest Ridge School of the Sacred Heart. She's the recipient of the ACM, Association for Computing Machinery, Best of 2014 Notable Article Award, and is a member of the winning team of the Yahoo Learning to Rank Challenge. So we'll now hear toward a quantum revolution for computing, and that'll be followed by our usual Q&A.
Is it on? Are the slides projected? Okay, great. Oh, wonderful. Well, it's an absolute honor to be here today, and an honor to be able to tell you about my research and the ongoing work in the field of quantum computing. It's a very, very exciting time in this field, and I hope you find it exciting as well. The prospects are great. So I'll tell you about quantum computing and how we believe it will literally overturn our notions of computing and how it will transform our digital age. So I want to start with how quantum computing came to be at Microsoft. So here is a picture of Michael Friedman. He's a Fields medalist, a topologist, a mathematician, and in around the year 2000, he was at Microsoft Research and actually heard a talk on knot theory. And there was another physicist at Microsoft Research, Alexei Kitaev, who was working on some amazing physics around topological anyons and these exotic quasi-particles. And the two came together and realized this might be a way one could compute in a quantum way. So in 2000, Mike started thinking about topological quantum computing, and shortly thereafter approached our then CTO, Craig Mundy, and said, I think we should form a lab around this, a theoretical lab focusing on condensed matter physics to advance the state of quantum computation. And so began Station Q, our lab and our center for studying quantum computing. My group is part of this lab. We in fact have a worldwide consortium looking at quantum computation. So we have Quark, Station Q Quark, which is my group in Seattle, in Redmond, just outside of Seattle. We have the Santa Barbara group where Mike Friedman is located. And then we have university partners around the world looking at how you actually build these devices. How do you build a qubit? How do you stabilize it? And then how do you scale it? And so that occurs at our university partners' labs. So Microsoft actually has quite a growing effort in this space, as do many other companies right now, which is why it's so exciting. There's quite a lot of investment now and interest in this field. So why do we care about quantum computing? Well, computers actually date back a very long time. This is the earliest computer I can find on record. This is a mechanism. It dates back to 100 BC, and this could roll and mark, say, time or input or products, trade, but you'd have to roll it and you'd have to know what you're counting on it, right? It wasn't exactly programmable. But then we made, one can look towards the difference engine. This was an advance in computing. One could start to think about actually asking it to do a problem, arithmetic, for example. And this, of course, was recently rebuilt and is at the Computing Museum. But it wasn't really fully universal and programmable, right? It was still specific. But then we come to the ENIAC machine, a very important machine in our history. And the ENIAC was actually, could be considered the world's, first really programmable device. And from there, in more recent history, we have large supercomputers, amazingly powerful machines, and now we have, for example, the Tiane, which is even faster than the Sequoia that was done by IBM in 2012. But these machines, as the mechanism couldn't compute everything we would want to compute, it was not universal, it was not programmable, still, the supercomputer will not be able to solve everything we hope to solve, right? So digital, as we move towards digital computing with the supercomputer, with our laptops, with our cell phones, these digital chips will not be able to solve everything we hope to solve, right? There are some problems that will remain hard, at least we think P does not equal NP, but we believe that there are very, very hard problems, and there are some problems that will take exponential time, times longer than the lifetime of our universe to find the solution. That will be true even on a supercomputer. So not all problems are efficiently solvable. But some problems that we find hard on our digital computers are in fact much easier if you move to a different type of device, a different type of encoding, a different type of storing, a different way to store information. And so we look towards a quantum computer to solve some of these problems. And at Microsoft, we look at what's called a topological quantum computer, which is just one path towards realization of such a device. So I want to tell you about what these problems are that quantum computers could solve. So some problems are very hard, and they're designed to be very hard for good reason. For example, they provide us protection. They're the mainstay of e-commerce today. Every time you're putting your credit card on the internet, it's being encoded, encrypted, for example, in RSA. So here's an example problem. Does anyone know what two prime numbers I multiplied together to get this number? Well, I'm glad everyone's giggling. That's a good sign. So this is a 2048-bit number. It's a very big number. And if you knew that answer, you could win something like $750,000. RSA would award you with that. And in fact, you'd probably be awarded with a lot more than that, because it would mean you've broken RSA, this cryptosystem that we rely on. And so finding these two prime numbers, it's a very hard problem. Now, how hard? Classically, if I use all of the world's compute power, digital compute power, this would take 1 billion years. Now, let's think about using a different type of device, a quantum computer. A quantum computer is thought at scale to be able to compute those two numbers in 100 seconds. Now, this is why quantum computing might be interesting. Of course, interesting for certain groups, right? But it's interesting that this quantum mechanical device can go and attack and solve a number theory-based problem, right? That's quite revolutionary. And Peter Shor, it was a miraculous discovery or development that he came up with Shor's algorithm, the algorithm to break factorization on a quantum computer, which in turn breaks most, if not all, of our current public key cryptography systems. Now, if we look at how this actually scales, why is this so different? Just to give you an idea, even if I move to a 4,000-bit number or an 8,000-bit number, a lot of people would say, we'll just move to a larger key size. But moving to a larger key size will not help you here because the scaling of the algorithms is fundamentally different. There's a gap. So if we look at the number of bits that we want to factor, and then the time to factor, the classical algorithm we have today, which is based on the number field sieve, it scales like this. It scales roughly exponentially. In computer science, it actually scales slightly sub-exponentially, but for all purposes, it's mostly exponential. And then the quantum algorithm scales polynomially. So you have this fundamental difference in the scaling. And even, here's the number we just looked at, a 2048-bit number. But you can see even if we move to a 10,000-bit number, the quantum computer will still be able to solve this. The classical computer, of course, is off the chart. So this is of interest, but again, this is a very special problem and may be of interest only to certain groups of people. So Feynman, if we go back to Feynman, you can actually go back to even his lectures in the 1950s, his lecture, Plenty of Room at the Bottom, and see that he was already talking about the fact that information is actually physical, matter is made of particles, we can study many paths simultaneously, and in his 1980s lecture, he actually began to say, what better way to simulate physical systems that live in large Hilbert spaces than with a quantum mechanical device, right? Let's actually use the type of device that these problems need. Let's make a device that relies on quantum mechanics to study quantum mechanics. Why ask a digital classical mechanical device? Why ask it to solve quantum mechanical problems? So he was thinking about this in the 1980s and even earlier. And so what he was talking about is, can we simulate physical systems on a different type of machine, say on a quantum computer? And if you look at how much time we spend simulating physical systems today, it's actually quite a lot. It's almost 50% of all supercomputing time is devoted to solving problems that we could, for example, solve on a quantum computer. And these are just the problems that we know how to solve on supercomputers today, right? There's a whole class of problems that we don't solve on supercomputers because the runtime will be billions of years, right? So here we can look at solving problems, for example, in material science, in chemistry, on a quantum computer. So let's take a look at what this means. So if we want to find the ground state of a molecule, let's take, for example, ferredoxin. So ferredoxin is actually used in energy transport and photosynthesis. And I chose this molecule because IARPA actually had a grand challenge to say, how long would a quantum algorithm take to find the ground state of this molecule? So the classical algorithm is exponential time to find the ground state in this case. And basically that's intractable from our point of view. Now we did, in 2012 when we looked at this problem, we had a so-called efficient quantum algorithm, efficient by computer science standards meaning it's polynomial time. So it's n to some power in terms of the scaling. But the problem is when we actually computed what that degree of the polynomial was, it was 11. Now n tends to be 100 for these problems. 100 is about the realm where we can't solve it classically efficiently. So 100 to the 11 is a large number. And in fact, when you plug in clock rates, predicted clock rates for quantum computers, this would scale like 24 billion years. So while this is considered polynomial time and efficient compared to the classical algorithm, it's not efficient enough for us to see a solution. But we worked on this algorithm for several years with colleagues and looked at improving mathematical bounds, actually simulating it in our software platform, which is called liquid. And by simulating it and finding better scalings, finding circuit optimizations, taking some compiler optimization techniques to improve the scaling, really making algorithmic improvements, we were able to go down to something that now scales like n cubed, and plugging in the same clock rates, you have now something that takes 1 hour to solve on your quantum computer. Now this is really interesting. This is a killer application for a quantum computer, right? Studying ground states of molecules, studying reaction mechanisms, understanding catalysts better. So let's dig into this a little bit more. Applications of simulating physical systems include, for example, better understanding nitrogen fixation, right? For nitrogen fixation, we want to produce ammonium. And this is a main way we produce artificial fertilizer, right? This can change food production around the world. And with roughly 100 to 200 computational qubits, one can begin to study the reaction mechanism behind this process to outperform the Haber-Bosch process. That's the process we use today. It was invented in, I believe, 1909, right? So with all the computational improvements we've had, we have not actually changed that process. It still uses huge amounts of temperature, huge amounts of pressure, and something around 1% to 3% of the world's natural gas just to produce artificial fertilizer. So we'd like to improve that and find a more efficient way. And with a quantum computer, we can study, for example, nitrogenase, the enzyme. And we know bacteria perform this process very efficiently. So we can study and determine if there's a catalyst that could improve this process. Now, similarly, with a quantum computer, we can use the same algorithm, same setup, to begin studying carbon capture. Again, seeking a catalyst, studying catalysts that might help us actually, capture carbon in kind of ambient spaces, not just at fossil fuel sources. In material science, it's quite exciting. Quantum computers are very good at simulating materials. If you want to study, say, the Hubbard model, right? This is a way of studying materials for room temperature superconductivity. If we can find a room temperature superconductor, we have hope for, say, lossless power transmission, for transporting power from Phoenix to Boston in the middle of winter, right, without any loss. And we can design the next version of the quantum computer, which is quite exciting. We have to use superconductors, and they have to be very, very cold. Millikelvin temperatures is where our quantum computer operates. So not only would this help us with energy, but it would help us design quantum computer V2. And in machine learning, this is an area that's on the horizon that we're just beginning to dig into. It's become a very hot topic, not only in the classical world, but also in the quantum world. We're looking at quantum machine learning algorithms, and what can quantum computing, what can quantum terms, what can quantum models actually give you in terms of modeling classical data or quantum data, right? But in the classical data case, we know that we can get speed-ups for training models, whether that's models of speech or text or web data or pretty much anything you can think of that you want to model. We know that we have improvements, for example, for training deep learning models and Boltzmann machines. So you may ask, okay, but what's underneath the hood? So I want to just take a few last minutes to tell you a little bit about how this computer operates. So classically, we have bits, and these bits store information. And when you store information in bits, it either takes the state, we have the state 0 or 1. So binary, 0 or 1. Everything is a string of zeros and ones. And so let's represent that this way. This is a quantum mechanical notation called a ket vector. So this actually represents a vector, but just you can consider it state 0 and state 1. So the light is either on or off classically. It cannot be both. Now, quantumly, we actually have something called a superposition. So our state can simultaneously be in 0 and 1. So we can represent that with a plus. It's 0 and 1. It's in a superposition, a linear superposition, but a superposition of these states on and off, for example, or spin up and spin down. So you can see this is starting to be something different than what we have classically. So we encode this information, this state, in the state of a two-level quantum system. For example, that could be the state of a single atom, the ground state and an excited state, right? It could be the spin, spin up or spin down. It could be, in our case, in topological qubits, it's stored actually in this quasi-particle state of being simultaneously an electron and a hole. But there's several paths towards realizing this. And we also have the ability to compute, right? So classically, we have 0 or 1, and to compute, to perform logic, we apply, say, a NOT gate, an AND gate, an XOR gate, so we can flip the bit from 0 to 1 and from 1 to 0. Now, quantumly, everything has to be reversible. So this puts a constraint on the operations, but mathematically, this means we have a unitary matrix. So instead of having a truth table, as we might classically, we have a unitary matrix, and this is our ket vector, a unitary matrix applied to the state vector. And we can visualize this on a sphere, what's called the Bloch sphere in physics. So North Pole and South Pole are 0 and 1. So that, our classical states are restricted to that. And quantumly, we can rotate to any other point on that sphere. That's a rotation. That's our computation. So we compute by rotating this vector, by applying, say, pulses or other signals to our quantum information. And this grows into a very, very large system when we have many qubits. So what this means is with 250 qubits that are entangled, that are interacting, that takes 10 to the 80 classical bits to store. That's huge. More atoms than are in our universe for just 250 qubits. So that's a huge amount of power. So n interacting qubits, we need 2 to the n bits of information to store that. So we want to harness that power. Of course, there's no free quantum lunch. We have a no cloning principle. We can't just make copies. And we have a readout. We measure the state. And so when we measure, everything is probabilistic. It collapses to one of the entries. So if we have our computation and then we measure, it collapses to 1. So we have to design our algorithms very carefully, and this is a great challenge and a lot of fun to figure out how we can do it. As part of that process, we've built a software architecture to allow us to actually program a quantum computer, to compile to it, and then also to simulate it and the circuits in advance, and then also to send them to hardware. So we can test, we can rapidly innovate on the algorithms and the device side. And actually, we've released this on GitHub to encourage more people, especially younger people, like undergraduates. We need more people in this field. We need people knowing how to program a quantum computer. And so we've released our software platform, Liquid. And this is, these are the spaces we hope to have impact. Privacy and security we talked about, impact on energy, the state of our environment, machine learning, and a quantum computer will sit in the cloud as an accelerator for your digital computers. So digital computers will not go away. We still need them to control the quantum computer. And the quantum computer will sit in the cloud as an accelerator, just like FPGAs or GPUs today. And I'll leave you with a picture of what it looks like today. This is our collaborator Charlie Marcus's lab in Copenhagen, Denmark. This is his lab. It's beautiful, Danish hardwood floors and brass clippings. This is the only lab that really looks this nice. And then you see the dilution refrigerators here being controlled by classical, digital devices. This is a large dilution refrigerator. This is the inside of it. So when you remove the shield, you have colder and colder environments going down, and then the quantum chip sits at the very bottom in around 20 millikelvin temperature. And then all of these control electronics come from room temperature, go down to the cold, and actually allow us to control the device. So this is pretty exciting that these exist. And thank you very much for your attention.
Okay, thank you. I guess this gives new meaning to the old expression, beauty is in the eye of the beholder. So we have time for questions, and wait for the mic. Right there.
Yeah. Rich here from Indiana. I take it that there's been remarkable advances in how to make a quantum computer work if only you had enough qubits that would last long enough to do the job. And I'm wondering if you could say something about what the current state of the art is and what the prospects are for having enough qubits that'll last long enough to do it.
Yes, it's a great question, and it's a very exciting time in terms of the hardware. So currently, the state of the art is let's call it in the 10 qubit range. So IBM recently put a quantum computer online. If any of you want to program a real quantum computer, it's online. It's 5 qubits. And then Google has roughly 9 qubits. Those are both superconducting qubit devices. And their plan is to have 50 qubits in roughly 1 to 2 years. In Microsoft's system, we have kind of part of a qubit. We have discovered this new quasi-particle, so we had to actually show a Majorana zero mode, which was this Majorana fermion. And now it's kind of half a qubit because we need 2 of them, 2 sets of wires to build a qubit. But we believe the scaling of that qubit system will be more rapid. So 50 qubits in about 2 years is where all of these technologies are headed. And then people believe that because it's done in a style that can be tiled and architected more readily, that soon after you'll have 100,000, say, I don't know, in a 5 to 7 year time frame.
Yeah, first in the back.
Ruth Schwartz-Cowan from Irvington, New York. I have an old-fashioned energy question for you. How much energy does it take to do an hour of computing this way, and how is the energy being generated in the various labs that have these quantum computers?
Right, so the nice thing is the computer is reversible. So actually when people looked towards conserving energy, they looked towards reversible computing. So in that sense, we have some conservation. The control electronics, it's a good question. My colleagues probably can answer your question better because they study actually how much heat dissipation is occurring going from room temperature to cold, and how much energy is required to actually maintain this cold temperature. So I don't know the exact answer, but I know that my colleagues are working on that. And they have some really, really amazing technology with some superconducting cables that are quite compact and don't dissipate much heat at all to conserve energy. So I'll have to get numbers to you. I don't know the exact numbers.
Erwin Shapiro, Cambridge, Mass. Fascinating talk.
Thank you.
I was wondering, I was struck by one of your quantum computing algorithms where in 3 years you made something like a 10 to the 13th or so reduction in the time required. I wondered if there were any general principles that are known that could be applied to say, now we can stop looking for better algorithms because we've reached the limit. We can't go any better. Are there any such general algorithms, any such general principles that govern the algorithmic aspects?
Right, so in general, we would seek a lower bound on the problem. In this case, we actually see that we're not quite at the lower bound, so there could be more improvements to the algorithm I showed. So when we simulate the different molecules, we can see that in simulation versus the mathematical bounds we actually have, the mathematical scaling, there is a small gap. And so we believe we should be able to prove even better bounds, but even if we might not be able to prove that, we do know that in practice our algorithms are scaling even slightly better than this. So we continue to look for, in terms of principles, it's come from kind of improved proof methods, but as well as improved circuit optimization techniques. So these circuits have kind of sandwiched gates that you can commute and move around and replace with other, other sets of logic, and this can help collapse the depth of the circuit. So those techniques we're applying to other algorithms as well. But indeed, I think there's further improvement here.
Okay, first in the balcony then.
Judith Shapiro, Bryn Mawr. I have a very simple question, an ethnographic question, and that is that in some of your slides we saw the appearance of chalk and blackboard technology. And I'm wondering whether at this point those are historical artifacts or whether in the ongoing work of you and your colleagues such technology still plays an important role.
Well, indeed. I think, Mike Friedman special ordered all of the blackboards from Germany for Station Q. So indeed, we still love the feel and just how it feels to write on the blackboard. It feels very inspiring. So they have blackboards, but we have whiteboards at Microsoft in Redmond. So.
Jerry Oestreicher, Columbia. You spoke eloquently of the promise of this technology, and you used phrases like, you can put this into your quantum computer, et cetera, and move. And so I was wondering what the current state of it actually is. In other words, if you were to take the fastest quantum computer that actually exists, that can be used now, and the fastest digital computer that actually exists now, what's the ratio of their power?
Well, I'd say your digital computer will do far more than your quantum computer.
By what factor?
Oh, it depends on the problem. But for example, we can factor, the number 15 on a quantum computer, but you can do that, instantly. You don't even need your digital computer for that.
3 and 5, I just
Yeah, exactly. So, at present, the goal is not, with this number of qubits, we don't expect to outperform a digital computer. The performance and the case, what we want to show is what's being called, it's not the greatest term, quantum supremacy. We want to show quantum supremacy, and the proposal is that at 40 to 50 qubits, that will occur. And that is going to be, some initial experiments around that are to show you can kind of measure a different distribution using your quantum computer than you can on your digital computer. And that's going to be a problem that requires a supercomputer running for months, and the quantum computer will find that in a few thousand runs, which maybe will take a day.
The reason why I asked it is the last time I asked the person in your position was several years ago, and the biggest number they could factor was 6. So there's been a fair amount of improvement.
Right.
Other questions? Okay, thank you very much.
Thank you.